Now that we've done exponential functions, it's time to take a look at logarithmic functions, which are in some sense the opposite of exponential functions, as you'll see. Today's main thing is to just kind of get used to writing and reading these darn things. So what's a logarithm? Let's kind of do it this way. I'm going to give you a fact. If you took the log base 10 of 100, you will get 2. Okay. Now we have to ask ourselves what's going on here. So when we say log base 10 of 100, one way to look at it is to say, okay, I've got a 10. I want to put an exponent on the 10 in order to get 100. What's that exponent going to be? And the answer is 2, because 10 squared is 100. So this is called the base of 10. And so again, when you say the log base 10 of 100, the question is 10 to what power is 100? Okay, like I say, it's kind of like the opposite of an exponent, because you're not given the exponent, you're trying to get the exponent. What is the exponent? I'm going to elaborate just a little bit, and I'm going to say, by the way, what's this symbol mean? It means that both of these things mean exactly the same thing. It's called equivalent. That's a symbol that means equivalent. To say one thing is to say the other. One follows from the other. So it's equivalent. It's equivalent to say that 10 squared is 100, right? Because that's kind of what I was trying to say there, is that you take 10, you raise it to the 2 power, you get 100. Take 10, raise it to the 2 power, you get 100. So those are exactly equivalent statements. Now looking at those, I'm going to introduce something I call the swooshy move. 10 to the 2 power equals 100. Swooshy, not sushi. Swooshy move. I've been doing this for a while, and then somebody informed me that, oh yeah, that's the way they do it in California. I'm like, okay, cool, whatever. I don't know if they say swooshy move in California, but anyway, that's the idea. So when you're looking at log base 10 to 100, think in terms of going in a circle. Start at the bottom here at the base and say 10 to what power is going to give me 100. Okay, 10 to the 2 power is going to give me 100, and so the answer is 2. Now, let's do some more examples. Log base 2 of 16. Well, you had to ask yourself, 2 raised to what power is going to give me a 16? So you just kind of work in your head a little bit, and you say, well, if I take a 2 and square it, that's a 4. If I take a 2 and cube it, that's an 8. If I take a 2 and I raise it to the 4th power, there we go. 2 to the 4th power is 16. Bunch more examples. 3 to what power is 3, right? Trying to swoosh. 3 to what power is going to give me a 3? Well, wouldn't you just raise 3 to the 1 power? So log base 3 of 3 is actually just 1. You might want to pause and try the rest of these, see if you can figure them out. And if you get stuck on any, start playing again. This one, log base 4 of 1. 4 raised to the power of what? I would have to raise 4 to what power to get 1? Well, that's where a 0 comes in handy. 4 to the 0 power is 1. 5 to what power is going to give me 1 over 25th? Well, notice 5 squared would get you the 25, but I want it flipped over, which means I actually want a negative exponent. So that's a negative 2. 5 to the power of negative 2 would give me the 1 over 25. Okay, cool. Coming over to example, what is this? Looks like I misnumbered them. That's a 5, that's a 6, that's a 7. Okay, looking at example 5 over here. 16 to what power? Now remember, we're talking about exponents. What exponent? 16 to what power is going to give me a 4, right? Now, you'd have to take the square root of 16, really. But that means the same thing as having an exponent of a half, right? 16 to the half power would mean square root of 16. And so you would get 4, so that's a half. 16 to what power gives me a 2? Well, that's a square root followed by another square root. That's actually a 4th root. The 4th root of 16. 2 times 2 times 2 times 2 is 16. 16 to what power is going to give me a half? Well, we figured out that if we took the 1/4 root, we would get 2. But we don't want 2. We want 1 over 2. We want it flipped. And so the exponent should be a negative 1/4. So log base 16 of a half is negative 1/4. Kind of funky, right? Kind of funky. And then the last one. Yeah, you can have a fraction base if you want. I don't see it very much, but it can happen. So a log with a base of 1/7. You have to raise 1/7 to a power. 1/7 to what power? That's a question mark. Is equal to 49. Well, you can get a 7 into a 49 if you square it. Now, that's a 1 over 7, so if you want to flip it over to a 7 first, you'd have to use a negative exponent. So this is going to be a negative 2. Come on, you. Erase. It's going to be a negative 2. Okay, so that's the basic way to read or work with or evaluate a logarithm. It's all about the swooshy move. 4 to the 0 power equals 1, and so on. Okay, now a couple of special notes here. There's 2 special logarithms we need to know about. If you see log of x written like this, it's supposed to mean that the default base is 10. So if you see a log by itself like this, it means log base 10 of x. And I'm going to put here in a math class or in a math book. Not so much the internet. The internet is a weird place. It's like people just do whatever they want on the internet. It's crazy. If you see this one, this is an ln. Natural log. It means natural log. It means the base is e. So if you see a natural log of x written like this, ln of x, that means that it's a logarithm and the base is that special number e, Euler's number, which we saw in the last one. So again, if you see a log with no number written, then in this course anyway, you're going to assume that it's a 10 for a base. Whereas if you see ln anywhere in the world, natural log means it's an e for a base. So those are the 2 special cases. And you should have a log button on your calculator. Sometimes this is called the common log. Maybe I'll write this down. Common log. And there's a button on your calculator which looks like this, and that's the common log. There's also a button on your calculator that should look like an ln, and that means natural log. So you got those 2 log buttons for sure on a scientific calculator. Okay, now that we kind of have some idea how to play with logarithms, what we're going to do is go back and forth between logarithmic forms and exponential forms of equations. So let me scroll to the top first. Basically this. So remember the swooshy move idea. This to this power is equal to this. I can write it this way, I can write it this way. Those mean the same thing. So if you've got this logarithmic equation, because x is in the logarithm, you can recast it, so to speak, as an exponential equation by 7 to the 2 power equals x. Cool. I guess you just solved it. X is 49. But you can take this equation and you can go like this. X to the 3 power is equal to 27. So I guess if you solved, you'd say x equals 3. 5 to the what power is 25. So that would, I guess by looking at that, you can say, oh, x must be 2, right? So sometimes in order to solve a logarithmic equation, you just rewrite it as an exponential equation, and then it's easier to look at. Example 12, what would happen here? We want to do a swooshy move. Well, remember, if you see an log in a math class, the base is 10. So we would say 10 to the 4th power equals x. 10 to the 4th power equals x. So x is 10,000, basically. And then this one, you want to do a swooshy move. You want to start at the base and come around like this. Well, if it's natural log, the base is e, so it's e to the power of 5 equals x. And usually we'll just write it that way. You could do that, you know, go on your calculator, type in 2.71828, raise it to the 5th power, or better yet, find the e button on your calculator, raise it to the 5th power, get a crummy decimal out of it. But usually e to the 5th looks really, really good. We'll leave it that way. You can go the other way. You can say, well, here's an exponential equation, 10 to the x equals 6. Now you can't really solve that in your head, can you? 10 to what power is 6? Well, 10 to the 1 is 10, that's too big. 10 to the 0 is 1, that's too small. 10 to the 1/2 would be the square root of 10. I'm just curious now. What's the square root of 10, folks? The square root of 10 is like 3.16 or so. So to get to 6, we'd have to be sort of in here somewhere, which means we'd have to be somewhere between 1/2 and 1 for our exponent. Okay, you're not going to do that in your head, is the point I'm trying to make. We're expecting something between 1/2 and 1, but how do you get it? You get it by saying, look, let me write this as a logarithm instead. So set yourself up like a little coat hanger or wireframe, whatever you want to call it. An empty log equals a something. And now take this and use the swooshy over here. 10 raised to the x power has to be 6, right? 10 to the x power equals 6. 10 to the x power equals 6. Okay, they both say the same thing. Now, how is that helping? It's helping because, like I was just saying, we have a log button on our calculator. We can take the log of 6. You just type that on your calculator. Use the log button. That's what a log base 10 is. It's sometimes called a common log. So the log base 10, it turns out, of 6. So the log of 6 is, I'm getting just about 0.77815 or something, just to carry 5 digits. 0.77815, that would be the answer. You want to see if it works, then what you do is you say, is that really right? If I raise 10 to the 0.77815 power, what am I getting here? I'm going to do that just for fun. 10 to the power of 0.77815, I'm getting 5.99998. See why I hate decimals so much. We're supposed to get 6, but we're getting 5.99998. So whenever you round something off, it means you've lost accuracy. But it's close enough to believe it, ain't it? Yeah. So it seems like 0.77815 is pretty much a good approximation to our answer here. So that's actually one of the main values of logarithms. You have an exponential equation. X is up in the air. X is in the exponent. How in the world are you supposed to solve for X? You can't get it by itself. You can't. How do you get it on the ground? Well, actually, there is a way to get it by itself and get it on the ground. Is to recast it using logarithms. I'm going to do the same thing for the next one. E to the x equals 6. Well, first you set yourself up an empty logarithmic equation like this. Then I like to change colors and say, okay, I got a swoosh. E to the x power is 6. And the reason that's doing us some good is because we have a natural log button on our calculator too. Right? Log base E means natural log. So it's the natural log of 6. So just use that other button. Natural log of 6. Boom. 1.79176. 1.79176 approximately. And if you want to test it, you can come back over here and go e to the 1.79176 and see what you get. Let's see now here. Not pi e. E to the 1.79176. This calculator is telling me that it's just about equal to 6.000003. So yeah, that is just about right. Let's get just a little bit fancier. Even if you have an equation that looks like this, definitely a little fancier, you can solve it by saying, let's just recast that as a logarithm. Put up a blank logarithmic equation. Get ready to enter my goo in there. So it's e to this power equals this. E to the 2x plus 1 power equals 5. Here's how I'm going to solve this. I'm going to say, okay, the left side says natural log of 5. The right side says 2x plus 1. First, let me just trade sides. I like having x on the left. It makes me happy. So I just traded sides. Okay. All you got to do is subtract 1 on both sides, which we usually write it this way. Because if we wrote it this way, it's like, wait, do you want me to subtract 5 minus 1 and then take the natural log? Or do you want to take the natural log and then subtract 1? What do you want to do here? So usually, just to avoid any question, any ambiguity at all, we just put the -1 in front. But then divide both sides by 2. So here's a really nice answer. -1 plus the natural log of 5 all over 2. Yeah, I could have pushed the button on my calculator, what's the natural log of 5, but I'd end up with one of those gross-looking decimals. My answer would lose accuracy, so let's just not. Okay, cool. So I hope you're starting to groove on these logarithms. First of all, they're swooshy move to figure them out, but also swooshy move can help you actually solve equations. If solve exponential equations, if x is up in the exponent, swooshy move can sometimes save the day for you. You will end up solving for x. Now we should graph these things. How does the graph of a logarithm function compare to the graph of an exponential function, or to anything else for that matter? So, believe it or not, I'm going to bring back the 5 amigos, but I'm going to do it backwards. Okay, what am I talking about? Here's my x, here's my y, right? So remember when we were doing exponential functions, we said, just plug in x equals, -2, -1, 0, 1, and 2, right? That worked pretty good for exponential functions. It doesn't work so good here. How am I supposed to find the log base 2? How am I supposed to have a pen? Okay, how am I supposed to find the log base 2 of -2? 2 to what power is -2? You'd be forced to hit the button on your calculator, get a crummy decimal. That's no good. So what we do instead is we do it backwards. Put those over there. Put those in the y column. Why does that help? Well, we're trying to graph y equals log base 2 of x, which is kind of the same thing as saying log base 2 of x equals y. So when I plug in y equals -2, 2 to the -2 power equals x. Get it? 2 to the -2 power, square it, flip it, you get a fourth. 2 to the -1 power is a half. 2 to the 0 power is 1. 2 to the 1 power is 2. 2 to the 2 power is 4. When we were graphing exponential functions, we had the points x is -2, y is a fourth. X is -1, y is a half. X is 0, y is 1. But notice now we're getting these same coordinates, but flipped backwards. So when x is -1/4, y is -2. So that's actually somewhere down here. When x is what did I just do? I read it wrong. That's what I did. Okay. Try this again. When x is 1/4, y is -2. So it'd be like down about here someplace. When x is a half, y is -1. When x is 1, y is 0. When x is 2, y is 1. When x is 4, y is 2. It goes something like this. Now if we were to graph 2 to the x, let's do that in a different color. P.S. y equals 2 to the x. Remember what that would look like. If you plugged in x equals 0, you would get 1. If you plugged in x equals 1, you would get 2. If you plugged in x equals 2, you would get 4. If you plugged in x equals -1, 2 to the -1 is a half, and so on. And remember, we got this nice horizontal asymptote like this. Well, for this, so this is what 2 to the x looks like. Well, the log base 2 of x is this thing down here. And by the way, yes, there is a vertical asymptote. Is that reminding you of anything? Go back a few lessons. Maybe it was 66 or something. Notice how one of these, they're reflections across the diagonal here, right? These are inverse functions. 2 to the x and log 2 to the x are inverses. That's how exponentials and logarithms are related. You could say 3 to the x is the inverse of log base 3 to the x. You could say e to the x is the inverse of log base e to the x, otherwise known as the natural log of x, and so on. So an exponential base of 2 and a logarithm base of 2 are inverses. An exponential base of 3, a logarithm base of 3 are inverses. An exponential base of e, a logarithm base of e, they're inverse functions. So there's a very tight connection between exponential functions and logarithmic functions. So that might help you remember the graph. For many years, I would always say, well, I know what 2 to the x looks like, and I know that log 2 of x has to be the inverse, and that's how we would do it. But you don't have to do it that way. You can just take your 5 amigos and, again, do them backwards. Sub in -2, -1, 0, 1, 2, but put it in the y column, not the x column. Solve for x, and you'll get a nice graph. Interesting things. I'm just going to say, recall, any exponential function could be horizontally stretched to, let's just say, land on, so to speak, another exponential function. Horizontal stretches. That was the cool thing on page 1 of the previous lecture. 2 to the x and 3 to the x. You could get from one to the other with a simple horizontal stretch. Well, for logarithms, they're related by vertical stretches. So I'll say, well, logarithm functions are related by vertical stretches. You should be able to take, or you are able to take any, like you could take log base 2 of x and graph it. You could take log base 3 of x and graph it, and you would find that one was basically a vertically stretched version of the other. Okay, so that's kind of cool. That's interesting. What's this one? This one wants us to practice with our transformations again. What's next? Oh yeah. Okay, so let's do another graph of logarithms. Practicing with our transformations, like I say. So the first thing we're going to do is we're going to strip away all this extra gook, the 2 in front, the +1 in here, and we're just going to say, okay, the base, or sometimes we call it the parent function, is simply y equals the log base 2 of x, which is actually something that we already graphed in the previous page. But let's just make our 5 amigos table again. So again, I'm going to plug in -2, -1, 0, 1, and 2, but I'm going to plug them in for y. And so when I plug in -2 here, 2 to the -2 is giving me 1/4. 2 to the -1 is a half. That's a 1. That's a 2. That's a 4. Okay, that's my parent function. Now I'm going to make some transformations here. Let's make them in green. One transformation I have to do is I have to get that 2 in front. Well, that would be basically taking the log function and multiplying it by 2. That's one of these kinds of things. You take your function, in this case this, you take your function, you double it. That was a vertical stretch by a factor of 2. Okay, that'll get your 2 there. Now, how do you get the 1 there? Well, you'd have to go inside the function, replace x with an x plus 1. That's our notation for that. Replace x with an x with 1. Do you remember what that does? That would go, let's see, left by 1. And so those are our 2 transformations. We should go a vertical stretch, and we should go left by 1. So let's come back to our original function over here and just kind of graph it in gray. So when x is a fourth, y is -2. When x is a half, y is -1. 1, 0, 2, 1, 4, 2, with a nice vertical asymptote here. So there, that was our basic function, our parent function, if you will. And now we're going to make these 2 changes. Stretch it and go left 1. In fact, maybe I'll do it in green. Stretch it and go left 1. Double the y coordinate and go left 1. Do this for every single point. This point. Double the y coordinate. So the y is equal to 2, so I'm going to go up to 4. Now go left 1. That point ends up there. This point. Double the y coordinate. It's a 1, so I double it to 2. Now go left 1. I'm over here. This point, double the y coordinate. Well, it's 0. It's still 0. Go left 1. It's here. This point, it's at -1. If I double that, I'll be at -2. And then go left 1. I'm over here. And just for good measure, take this point, which is at -2, double that y coordinate to -4, and then go left 1. You end up over here. Okay, now do that with the asymptote as well. You take the asymptote, you take these gray things, You double the y-coordinate, which does nothing. It just stretches it along the y-axis, I guess. But then you go left one, which means it's going to end up over here. So there's my new asymptote. And I can join my green points. I could put nice little arrowheads on there, you know. And wow, I've got a really nice graph of that function. Okay, so this is a nice way to make these graphs. Start with the basic function, because you know those points are going to capture it really well, and then just follow them. Where do they get moved to? Well, if you double it and you go left one, it's going to get moved over there. So there's those points right there, and you end up with a really nice graph. Okay, well, this is like another topic here. It's logarithmic related for sure. Remember how I did monsters and stuff with the exponential functions? Well, we're going to do stuff with the logarithmic functions. So it turns out logarithmic functions are related to half-lives. They're related to decibels. How does this work? Well, first let's just kind of look at this question here. Biff runs a 90-foot cable from his dish to his receiver. There's a 200 milliwatt signal coming in. What signal's coming out? Here's the thing. The cable loses half of its power every 30 feet. That's a sort of a half-life thing, right? It's a half-life. Half-life. You lose half your power every 30 feet. So in some sense, it's a half-life, not in terms of years, but in terms of feet. Every 30 feet, you're going to lose half your power. So I can actually kind of just do this. I can say, well, the input power, they told me, was, what was it, 200 milliwatts. Now, if I go to 30 feet out, the 200 is going to be 100, right? If I go another 30 feet out, now I've got a 60-foot length of wire, my 100 is going to be down to 50 milliwatts. See, you just keep cutting in half. Every time you go 30 feet, you cut it in half. If I go another 30 feet out to 90 feet, the 50 gets cut in half to 25 milliwatts. And that answers the question. He runs a 90-foot cable. Yep. 200 on the inside. Yep. What is it on the outside? The input side and the output side. It's going to be 25 milliwatts. So that's kind of how you can work with half-lives. You literally just say, oh, the half-life's 30 feet. Well, after 30 feet, cut it in half. After another 30 feet, cut the power in half again. After another 30 feet, cut the power in half again. That's really all there is to it in terms of like intuition or whatever. Now, what's logarithms got to do with this? Well, this is kind of interesting. Let's take the log of 200. Where should I do this? I'll do this here. Take log of the power. If I take the log of 200, and I'm just going to do that on my calculator right now. Log of 200 comes out to 2.3. 2.30. If I take the log of 100, come on you, log of 100, I'm going to get actually 2.00. If I take the log of 50, I'm going to get a 1.70 if I round to 2 decimal places. And if I take the log of 25, I'm getting a 1.40. Okay. What's going on with the logarithms? With the power, we'd say 200 divide by 2, divide by 2, divide by 2. We kept dividing by 2, dividing by 2, dividing by 2. Dividing by 2 on the power would, every 30 feet, the power would be divided by 2. It would be multiplied by a half. It would be divided by 2. But what's going on with the logarithm? The logarithm's only going down by a constant amount. Subtract 0.3. Subtract 0.3. Subtract 0.3. Subtract 0.3. This is interesting. Logarithms, and I'm speaking very loosely, turn division into subtraction. In other words, if you divide something by 2 over and over, the logarithm is going to go down by 0.3 over and over. Now, the 0.3, new color, PS. The 0.3 is called 3 decibels. deci is the prefix that means slide your decimal over one. So 3, if you make it a deci, you'd go like this. So anyway, think of it this way. Yeah, just it's 3 decibels. So to cut in half, so cutting power in half means subtracting 3 decibels. And that's the big mantra for this part of the lesson. Cutting the power in half means subtracting 3 decimals. I suppose you could say it the other way. If you double the power, means you add 3 decibels. Right? Because if you double the power from 50 to 100, if you double it, then you're going to add 3 decibels. So to go down is to subtract 3 decibels. To go up is to double is to add 3 decibels. Now the interesting thing is the 3 decibels doesn't matter where you are. The power could be 200. Well, if you cut it in half, you subtract 3 decibels. The power could be 50. And if you cut it in half, you subtract 3 decibels. Here, if you think of subtracting, you're subtracting 200 minus 100. But it counts as 3 decibels. Here you'd be subtracting 50 minus 25, but it counts as 3 decibels. So that dividing by 2, dividing by 2, dividing by 2 becomes, in terms of logarithms, in terms of decibels, it becomes subtracting. 3 decibels is 1 half-life. If you're going to be an ultrasound tech, you can't graduate without knowing that. 3 decibels is 1 half-life. Okay, so let's do that again. Bonnie's cable has P in equals 200, P out is 15 milliwatts. This represents a drop of how many decibels? Okay, so we'll just kind of try to do it the way I was doing it before, or say, well, I'm starting at 200 milliwatts, huh? Well, if I cut that in half to 100, that would mean down 3 decibels. And if I cut that in half to 50, that would mean down another 3 decibels. Notice I'm down 6 decibels. Minus 3 decibels here, minus 3 decibels here. So I'm down 6 decibels so far. If I cut the 50 in half, I'll be at 25 milliwatts. I just went down another 3 decibels. So I've gone down 9 decibels. If I cut the 25 in half, I'll be at 12.5 milliwatts. That would be going down another 3 decibels. Now, here's the thing. We didn't really want to go down quite that far. We wanted to go to 15. So 15 is like over here somewhere. So we could say 3, 6, 9, 12. We could say not quite 12 decibels. We go down by not quite 12 decibels. Yeah. Now, I should probably give you a formula, right? So there's a formula you could use. And the formula is perfect for if you're not going to land on an even, if you're not going to land on one of these numbers, you're going to need the formula. So the formula goes something like this. Decibels is, let's make sure I get this right, 10 times the log of P in over P out, like that. So if I were to put in that we started at 200 milliwatts and we ended at 15 milliwatts, notice the units must match. This doesn't work if you use volts and kilovolts or whatever. The units must match. But anyway, I did. The units match. So I'm going to figure that out now. Ask my calculator. 10 times the log of, and I've got to put a 200, whoops, I said whoops, 200 divided by 15 inside there. And it's giving me an just about 11.25. So we were saying not quite 12. Turns out, if you want a more accurate answer, it's 11.25. Nice formula, huh? You might want to keep your eye on that one or keep this one handy. That's a good formula to use when you're playing with decibels. It'll give you your exact answers. I do like to do it this way. I call it the back of envelope way, because you can see what's happening if you do it that way. Or you can grab a formula. Formulas bum me out because they're kind of mysterious. You know, who wants mystery? Okay, one more example here. What do we got? Bjorn's cable has a loss rating of 20 decibels every 100 feet. Okay. He inputs a 200 milliwatt signal to a 50-foot length. So what will be P out? Okay, here's the loss of the cable. 20 decibels over 100 feet. Well, we don't have 100 feet, we have 50 feet. So if I cut the cable halfway, I hope this makes sense, you'd have half the loss, right? You'd only lose 10 decibels over the 50 feet. Okay, we'll lose 10 decibels. Now every 3 decibels is a half-life. Every 3 decibels is a half-life. So this is a little more than 3 half-lives, right? 3, 6, 9. This is a little more than 3 half-lives. So that means that the 200 milliwatt input signal should get cut in half about a little more than 3 times. If you cut it in half once, you're at 100. If you cut it in half twice, you're at 50. If you cut it in half 3 times, you're at 25. And we want to cut it just a little bit more. So the answer is just under 25 milliwatts. That would be your approximate answer. If you're just out there installing cable on a satellite dish, you'd probably say, I don't know, maybe something a little less than 25. But if you want an actual answer from a formula, well, let's grab that formula out again. That formula said that the decibels is 10 times the log of, put the P in over the P out. Now the numbers that we have, we said 10 decibels. We're going to lose 10 decibels. 10 times the log of, the Pn is 200 and the P out is what we're solving for. So we have to solve that for x. How are we going to do that? Well, first thing to do is get the logarithm by itself. So if I divide both sides by 10, I'll have basically 1 is equal to the log of 200 over x. Okay, that's interesting. How are we going to solve that? Well, remember we have this idea of kind of like swooshy move. Remember page 1, we were taking exponential equations, turned them into logarithmic equations, and vice versa. In other words, log without an explicit number there is a 10. I can say 10 to the 1 power is equal to this. Well, 10 to the 1 power is 10, of course, is equal to 200 over x. Solve that for x. So this is like 10 over 1. So cross products, 10x equals 1 times 200. Divide both sides by 10. Turns out it comes out to exactly 20. Who'd have thunk it? Comes out to exactly 20. We were expecting a little under 25. We got 20. This is beautiful. Okay. So again, this formula front and center for playing with decibels. But I would so encourage you to just keep in mind 3 decibels is a half-life, because that can get you very close to the answer. That gets you a lot of partial credit. Let's put it that way. Okay, and then you can make sure that you used your formula correctly. You came out with the right answer. Okay, where are we? We got to pause.